Good day, everybody. Let's do a quick review about Chapter 10. In Chapter 10, we learned intermolecular forces. More specifically, we learned different types of intermolecular forces. For example, dispersion force or dispersion interaction. The second type, dipole-dipole interaction or dipole-dipole force or dipole-dipole attraction. The third type, hydrogen bonding, which is not exactly a chemical bond. It is intermolecular force, which is much smaller than the chemical bond. The fourth type we learned is ion dipole force or ion dipole attraction, ion dipole interaction. We're going to use these different kinds of concepts in this new chapter. In this chapter, we'll first go over how ions interact to make ionic compounds, and then we'll discuss how ionic compounds can be dissolved in polar solvents, to form a solution. And then we'll go ahead and talk about how the vapor pressure of these newly formed solutions behave. For this section, we'll be mainly focused on non-volatile solutes. So after that, we'll talk about the behavior for the mixture of volatile solutes. Then in the end, we'll be talking about so-called collective properties of solutions and how to use them to measure the molar mass of a solute. Ionic compounds are most likely to be solids at room temperature because ion-ion attraction between particles of opposite charge is one of the strongest interactive forces between particles. Actually, they are so-called ionic bonds. And the results in the formation of the ionic bond will be very, very strong. The strength of the ion-ion attraction or the chemical bond, ionic bond, is defined by Coulomb's law. See this equation in the circle. The energy of the Coulombic interaction depends on two factors: the magnitude of the positive and negative charges. And the second factor is the distance between the charged particles, represented by the distance d. And the distance d is related to the radii of the corresponding cations and anions. The relative magnitude of these forces will determine the melting points of ionic compounds and the solubility in water. Let's consider two examples. The first one is the table salt, NaCl. The second one is calcium sulfate, CaSO4. The charges on calcium ion and sulfate are twice as large as the charges on sodium and the chloride, because you have +2 and -2, +1 and the -1. So Q1 times Q2 for this is -1, and for calcium sulfate, Q1 times Q2 is actually 4 times as large. Now let's compare the distance, which depends on the corresponding radii of the ions. Sodium ion the radius is 102 picometer. Then when you compare that with calcium, it's very comparable. Calcium is actually slightly smaller in size. When you look at chloride, the radius is 181 picometer, which is slightly smaller than sulfate. The radius for sulfate is 230 picometer. According to the information we have over here, the d, or the distance between the cation and the anion for calcium sulfate is slightly bigger. However, because of the Q1 times Q2 is much larger than that of sodium chloride. So this results in a much larger overall result. In other words, the interaction between calcium ion and the sulfate is much larger than that of the sodium chloride. So the end result is this salt is actually less soluble in water than table salt. As a matter of fact, calcium sulfate is readily precipitated from seawater, much more readily than sodium chloride. Here you see a table of some of the monoatomic ions of the main group elements, and the ionic charges in the radii are used to explain the phenomenon, such as relative solubility, as we just explained, table salt NaCl versus calcium sulfate CaSO4. In general, the charge distance is almost always responsible for the larger difference in the strength of ionic interactions. So when we try to compare the ion-ion interaction, we always compare the charges first. If the charges are the same, then you compare the distance or the radii in between. So let's look at a couple of examples. Predict which salt exhibit greater ion-ion interactions. So we are given two pairs of ionic compounds. We want to predict which compound exhibit greater ionic attraction. According to Coulomb's law, you have two factors. The first, we always remember, we're going to analyze the charges first, because charges can change really quickly. It can double from +1 to +2, -1 to -2 very easily. But the radii cannot change as drastically. So when you look at the first pair, MgO and the NaF, the ionic charge will dominate the attractive force as we just analyzed. Always look at the charge first. For MgO, it's +2 and -2. So you have you have +2 and then -2. So when you look at the product between Q1 and Q2, it's -4. All right. Now you look at Na plus and F minus. The QQ value is actually -1. So in this case, the ionic charge will dominate as predicted. So we don't even need to compare the radii or the distance between the ions, because usually they cannot change as drastically. So MgO would exhibit the greater attractive force or ionic bond. For the second case, you have MgO and MgS, sodium oxide versus sodium sulfite. When you compare the charge product, Q1 times Q2 are exactly the same for both. So you will have to compare the distance in between, which depends on corresponding radii. Magnesium ion, in this case, is exactly the same. So you will have to compare the sizes for oxide and sulfide. Apparently, sulfide is bigger, resulting a bigger distance between Mg2 plus and S2 minus. So MgO will have greater ionic attraction than that of MgS, because the distance between MgS, between the charges in MgS is bigger than that of the MgO. Let's quickly summarize what we have talked about. According to Coulomb's law, the attraction depends on two factors. One is the charges, which usually dominates the attraction force. And the second is the distance. If the charges are different, we can simply compare the Q1 times Q2, whichever gives you a bigger Q1 times Q2, that will have the better or stronger ionic bond. If both give you the same Q1 times Q2, then we compare the D, or the corresponding radii for the cation and anion. Bigger distance gives you smaller attraction. Now we know when ions interact, they form ionic compound. Ionic compounds can dissolve in water because like dissolves like. Ionic compound is one of the extreme cases of a polar compound. It's so polar, the charges are separated. If we want to break down the dissolution process into 3 steps, we can write it this way. Originally, you have the solvent and the solute, which exist separately. Then the first step, you actually separate the solute. So this step, it's the ion and the ion that you're separating. You call this delta H ion and ion. All right. Then the second step, you separate the solvent molecules. So you separate solvent molecules. In this step, we call that delta H for the solvent, which is dipole-dipole interaction for polar solvents. Okay. So hopefully this can help you understand it a little bit more. Then the last step is, since you have separated both the ions and the solvent molecules, so now you can mix them together. So the last step, which is delta H for the mixing. Since when you mix, you form ion dipole. So that's why for this step, you call that delta H for ion dipole. We're not going to go into too much detail about this, but you do need to remember, for the separation of ions, it's going to be endothermic. It takes energy to break up the ions. Similarly, it takes energy to break up the intermolecular force between the solvent, for example, water molecules. And the last step, the ion dipole, is going to give you the enthalpy in that process is going to be negative. That's exactly why the ions and the solvent molecules, the polar molecules, will mix, because you give off energy in the last step. And we can actually define the enthalpy of hydration as the separation of the solvent, remember that's the solvent, and the delta H for the mixing. Okay, so if we rewrite this equation, it will become delta H for the solution will be the delta H for the solute, or ion and ion, and delta H for the hydration. All right, let's look at a picture about how this whole process actually works. When you separate ions, so this process is actually so-called a delta H ion and ion interaction. Then you're going to separate the solvent molecules. That's the delta H for dipole-dipole force. Then when you mix it up, it will form new ion dipole. In this process, we call that delta H for the ion dipole. All right. After you mix it up, that's the solution you actually see surrounding the negative charged ion and the positively charged ion. Okay? All right. That's about all the details you need to know. Now, I would like to introduce to you a new concept, which is called a lattice energy. Lattice energy is defined as the energy that is released when 1 mole of an ionic compound is formed from its free ion in the gas state. Notice the delta H for ion is exactly the opposite procedure, because delta H for ion is the enthalpy to break up 1 mole of ionic compound to the corresponding free ions in the gas state. So the magnitude for the lattice energy should be exactly the same as that for delta H ion-ion interaction, but the sign will be totally opposite. In other words, the delta H ion and ion is the same as lattice energy, but different in sign. So if you want to rewrite the whole delta H for the solution, which is defined as, so still remember the delta H for the solution, all right, equals the delta H for the ion and ion plus delta H for hydration. So remember, this delta H for ion can be written as negative U, or lattice energy. So when you rewrite it, that's why you have equations over here. Basically, this last equation relates the lattice energy with the delta H for the whole solution. Please remember, lattice energy is the energy that is released, and delta H for ion is the energy that is absorbed or required to remove the ions or separate the ions. So let's look at some real examples for lattice energy. When you look at this table, first you should realize all these lattice energies, they are energies being relieved, so that's why they all have negative charges, as you can see in this table. Second, look at the magnitude. When you look at the magnitude of this whole series, for example, you do notice MgO has the largest in the series. How do you explain this? We actually talked about it when we were talking about the ion-ion interaction using Coulomb's law. So the same way, when you compare the magnitude, you look at the Q1 times Q2 first, then you look at the distance. So usually when we compare this, we would emphasize it's the magnitude that we compare. For example, MgO would have a larger lattice energy in magnitude than KBr, which has negative 691, because as we learned already, we compare the charges first because usually they dominate. Now let's look at the hydration enthalpy. So what is hydration entropy? A quick review. Hydration, so when we write the delta H for the solution, it equals the delta H for ion and ion. That's the solute separation. Delta H for the dipole. Oh, remember that's the solvent separation. The last step is the delta H for the mixing. Or when you mix this thing, it forms ion dipole. Okay, so the last two steps, we put it together. We call this enthalpy of hydration. So when you look at the magnitudes, do you remember enthalpy of hydration? Enthalpy of hydration, delta H for hydration, it's also always negative. Or if you combine step 2 and 3, it will give you an exothermic second step. In addition, I hope you also noticed the magnitude of the enthalpy of hydration are also consistent with the factors mentioned previously for electrostatic forces governed by the Coulombic equation. Hydration energies are greater for the highly charged ions compared to the monovalent ions of the similar size. For example, when you compare the calcium ion with potassium, calcium ion is more highly charged, so the process is more exothermic, or the magnitude for delta H hydration is bigger. Look at another example. Look at magnesium, right? It's too charged. Now you compare that with the delta H hydration for sodium ion. Apparently, this is more negative for magnesium ion, or the magnitude for delta H hydration is actually bigger than that of the sodium ion. Remember, we're talking about magnitude or the absolute value without looking at the sign. Let's quickly summarize what we have learned for this small section. So when you dissolve an ionic compound, for example, table salt, into water, we can theoretically break down the dissolution process into 3 steps. First is the separation of the solute. That means you break up the ions. The second step, you break up the solvent ions, which has dipole-dipole interaction. Then the third step, you mix up the ions with the polar solvents. Then you have the ion-dipole interaction. That's why you indicate them as delta H for ion-ion, and delta H for dipole-dipole, and delta H for ion-dipole. Also, delta H for hydration is the last 2 steps combined. We also went over some of the details about how to compare the relative magnitude of the lattice energy and the magnitude for the enthalpy of hydration. So, what is vapor pressure? If you can recall, in chapter 10, we defined vapor pressure as the pressure exerted by a gas sample that is in equilibrium with the liquid. So what is the equilibrium state? Equilibrium state means the rate of the evaporation of the molecules from the surface into the gas phase equals the rate for the condensation from the gas phase back to the liquid state. In this figure, the chamber on the left side is actually at equilibrium because the rates of the evaporation and the rates of condensation, they are equal. In the chamber that is represented on the right side, the rate of condensation is the same, but the presence of dissolved solute, it decreased the rate of evaporation. So on the left side, you see a pure liquid. On the right side, you see solute being dissolved in the liquid, which makes the vapor pressure smaller at the equilibrium state. Okay? Let's emphasize it for one more time. When you look at the left side, which gives you pure water, the vapor pressure at equilibrium is actually bigger than that of the seawater, because in seawater you have sodium chloride and some other salts that's being dissolved, which decreases the amount of vapor that can be generated when it reaches equilibrium. As we just analyzed, the presence of the non-volatile solute will reduce the vapor pressure of the solution. What are some of the other factors? Temperature is another factor. If you have a higher temperature, the kinetic energy of the liquid molecules will be bigger. So more molecules will be able to escape from the bulk and become the gas molecules, which will increase the vapor pressure. The last factor is the intermolecular forces. This is related to the nature of the interaction between the solvent and the solute. So the stronger the interaction between the solvent and the solute, the higher kinetic energy is needed to for the liquid molecules to become gas. So the vapor pressure will actually decrease. Remember, when the solvent and the solute, they are more attracted to each other, they are less likely to break away from each other and become the gas phase, resulting in a decreased vapor pressure. Qualitatively, if we add non-volatile solute, for example, table salt, into the pure water or other solvents, the resulting solution will have a smaller vapor pressure. This can be calculated according to Raoult's law. So the resulting solution will have a vapor pressure which is indicated as P solution. It's the mole fraction chi, it's not an X, it's chi solvent, times the P pure or P naught. You don't have to write the solvent, but to emphasize that it's the P for the original solvent. Let's look at one example, how we do this calculation. So in this example, it's asking you the vapor pressure of the water over a solution that contains 60.2 grams of ethylene glycol and 62.1 grams per mole as the molar mass in 250.0 grams of water at 30 degrees. It also tells you for the pure water at 30 degrees C, it has a vapor pressure of 31.8 millimeter mercury. So how do we solve this problem? Apparently, according to Raoult's law, P for the solution is the mole fraction times the vapor pressure for the pure solution, for the pure solvent. So what we need to do is to find out the chi for the solvent, chi water, or mole fraction of water. So the first step, we will need to find out the moles for the solute. So it's the grams divided by the molar mass. This gives you 1 mole of the solute. Next, we will need to find out the moles of solvent, which is water in this case. So grams divided by molar mass, you have 13.87 moles of water. So now you can calculate the chi by dividing the moles of solvent by the total of the solvent and the solute. So that's the chi. This thing is the chi for the solvent. Okay? Times the pure water vapor pressure. That gives you a number which is 29.7. When you think about it, it does make sense because the mole fraction is always smaller than 1. You cannot have 100% pure water. If you have 100% pure water, it would not even be a solution, right? It would be a pure solvent like water, okay? If you want to see more examples, you can look at the complementary material. We have some problem sets over there. You can also look at that. So far, we've been emphasizing one thing, how the vapor pressure behaves when you have a non-volatile solute that is being added to a pure solvent to make a solution out of it. if you have more than one volatile component, then every component would contribute their own vapor pressure to the total pressure of the solution. So for this reason, in this case, the vapor pressure for the solution would be the total for the contributions for each component. For example, for component 1, which is volatile, you would have chi1 times P1 pure. And chi2, which is mole fraction for component 2, times the contribution from component 2. And you have the third component, etc. You just add the contribution from each component. Then you will be able to get the total for the newly made solution, which is slightly different from Raoult's law. In Raoult's law, you have a non-volatile solute, which does not contribute to the vapor pressure for the solution because it's non-volatile. But in this case, every component is volatile, which means they will contribute to the total pressure of the solution. So that's why you will have to add each contribution together as indicated. Let's look at the two-component system. All right. So the ideal situation would be if you have a contribution from component 1 and 2, the ideal situation for the P total would be this line when you add it together. That's a straight line as you see this dashed line over here. But sometimes the P total will be smaller than predicted, like you see in this purple. Okay? And sometimes it could be bigger. Okay? So what does it mean? Actually, you consider it this way. All right. The real situation is producing smaller P total than predicted by the ideal situation. What do you mean ideal situation? Ideal situation, that means before and after the mixing, the intermolecular forces between the solute and solvent and the solvent-solvent interactions is about the same as the interaction after you mix it, or it's about the same as the ion dipole. But most of the time, it's not going to happen. So when you mix up something, it's more likely the interaction is going to be smaller than you originally have, because the interaction between the like molecules would be bigger. So you would be most likely to see a positive deviation. But it could also happen after you mix the interaction between the solvent and another component, another solvent, or you can call that a solute, okay? Between the two components, the interaction between the two components could actually become bigger. If it becomes bigger than original, what does it mean? It's more attracted to each other. So it's less likely for them to escape the bulk liquid and become gas, or the P total will be smaller than predicted, than the ideal situation, which is that straight line as you see over here. Let's look at one example. In this example, certain amount of water is mixed up with ethanol. The first thing you got to pay attention to is both water and ethanol are volatile. So both of them will contribute to the vapor pressure of the resulting solution. So you will have to use the P total or P solution equals chi1 times P1 plus chi2 times P2, etc. So the first thing we need to calculate is the mole fraction for each component. So we know the mass and the corresponding molar mass. So we should be able to easily calculate the moles of each component. So this gives you the moles of water and the moles of ethanol. All right. So the total number of moles, as you can see, is these two added together. That gives you 6.092 moles. So now we should be able to calculate the mole fraction, which is defined as the moles of that component divided by the total number of moles. For water, it gives you 0.9109, and the other one would be 1 minus that. Or you can do the calculation, which gives you exactly the same number, 0.08908. So you total up the contribution for each component. The chi for water times the P water, and the chi for ethanol times the P for ethanol. So you put it together, it's 26.9 torr. All right. So the vapor pressure of the solution is like intermediate between the vapor pressure of pure water and the pure ethanol. The fact it is closer to the vapor pressure of water is consistent with the fact that the solution actually consists of way more water. It's 90% mole fraction of water.